Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the welding of metals. In this particular presentation I will be talking about the hybrid joining. Hybrid joining is about the bringing in two different kind of the joining or welding processes. For example, the adhesive joining clubbed with the solid state joining, adhesive joining clubbed with the resistance spot welding, solid state adhesive joining clubbed with the mechanical joining, say the riveted joints, nut bolts or the pins, or adhesive joining clubbed with the TIG welding, adhesive joining clubbed with the laser welding. So, this is one category. The second category is where adhesive joining the solid state joining is clubbed with the fusion joining, although this kind of combination is very rarely used. So, what we do, we mostly prefer to go for the adhesive joining clubbed with other joining processes as well as the hybridization of the fusion welding processes. Okay. So, but there are different objectives which are achieved through this kind of the hybridization of the joining processes. So, initially we will be talking about the following aspects like the need of the hybridization. There are many purposes which are realized. One is certainly to improve the performance of the joints, which may be in form of the load carrying capacity, fatigue resistance, okay, and improving the reducing the residual stresses. This is one aspect where the performance is enhanced. Another is like increasing the productivity. Okay. So, this is done by increasing the welding speed, increasing the deposition ratio, and by reducing the edge preparation requirement, increasing the thermal efficiency of the processes. So, there are many things that are realized. So, the performance is enhanced, this, and you see altering the structure and properties appropriately, so that the performance is enhanced. Okay. So, the performance enhancement can also be done by adjusting the structure and properties of the joints developed through the hybridization. So, these are the two main objectives that are realized through the hybridization. One is improving the performance and second is improving the productivity, so that the joints can be made at the low cost. Okay. So, this improvement in performance, as I said, this is based on the two aspects. One is increasing the load resisting cross sectional area. Okay. Increasing the load resisting cross sectional area, this is one aspect where some load resisting cross sectional area, for example, is developed through the adhesive joining, plus load resisting cross sectional area is also developed or introduced through the metal to metal joining or metallurgical joining. Okay. So, both these will be working together to increase the load carrying capacity or the desired mechanical performance. This is one. The second is increasing the productivity when the two different welding processes are brought together, especially in fusion welding process category or the fusion welding clubbed with the solid state joining processes. They help in increasing the welding speed, increasing the deposition ratio, increasing the thermal efficiency. So, all these help in developing the joints economically. So, our cost of producing the weld joint is reduced. So, these are the two main objectives as well as the ways by which the hybridization of the joining processes work. Okay. What are the different types of the hybridizations which are realized is the adhesive bonding clubbed with the mechanical fastening. So, here what we do, adhesive bond is developed, then this can be clubbed with the mechanical joints in form of like say use of nuts and bolts, use of rivets, use of pins. Okay. Then there is another one is, so this is about the mechanical fastening. Okay. Adhesive bonding clubbed with the mechanical fastening. Another approach is where adhesive bonding is clubbed with the solid state joint. So, here we can develop the lap joint using the FSW, say for example, or we can also develop the spot joint by the FSW. So, in this case both these will be helping to develop the metallurgical joint between the metallic components, apart from the load contribution coming from the adhesive bonds. Okay. Then we have the another the category, that is the adhesive bonding clubbed with the resistance spot welding. We know that the adhesive bonding is primarily used for developing the lap joints. So, here what we do, metallurgical bond between the two sheets to be joined is realized through the resistance spot welding. So, this is the zone where resistance spot welding is there, and other areas will where the adhesive bonding will be contributing. Okay. So, in this case the two approaches, either first the adhesive bond is developed, okay, adhesive bond is developed, then metallurgical bond through the resistance spot welding is created. Another one where resistance spot welding is made, then adhesive is filled in the gap at the interface for developing the joint. So, in this case both metallurgical joint and the adhesive bond both will be contributing towards the load carrying capacity, or they will be working against the service conditions. Okay. Now, the adhesive bonding clubbed with the fusion welding, that is also possible. So, here adhesive bond is made first, and then we use the suitable type of the heat source. This may be in form of the laser or TIG welding, non-consumable arc welding processes, like say like a non-consumable or non-filler type of the fusion welding process, where only the heat is used, the filler is not used. So, what we do, laser beam is focused at the interface. So, the melting at the interface is realized, coupled with the melting at the top. So, after the solidification, the top surface remains as it is, but the interface helps in developing the metallurgical joint. Okay. Same is true for our arc welding, only difference is arc is spread over a larger area. So, larger area is brought to the molten condition, followed by solidification, and that in turn will be helping to develop the bond. Okay. So, this is the say adhesive joint, adhesive bonded area, and when the arc is applied, the bond is developed in this way. So, here the top portion will be melting, followed by solidification. This is the zone where the metallurgical joint between the two sheets will be developed, and so and that is how the adhesive bonding clubbed with the metallurgical joint or metallurgical joint coming up due to the TIG or the laser welding, okay, between the two overlapping sheets. Okay. So, this is about the adhesive bonding clubbed with the fusion welding. Okay. Now, sometimes even solid state joining is clubbed with the fusion joining, and the main idea here is like the fusion welding process is primarily used for either preheating the parent metal so that it becomes soft, followed by the solid state joining like FSW. Okay. Or it can also be used for like the fusion welding is used for post heating, post weld heat treatment for improving the structure and properties and reducing the residual stresses. So, the fusion welding related processes like TIG or the laser kind of the heat source can be used primarily for preheating the parent metal or for post weld heat treatment, so that the stresses are relieved, or the steel if it is steel, so then that the metal is or the joint is tempered for improved toughness and ductility, residual stresses are relieved. So, but since the solid state joining process is based on the approach of developing the joint in solid state, so we try to avoid much of the heat supply from the fusion welding processes. The fusion welding processes are particularly clubbed primarily for the preheating or post heating, not for the development of the joint, but helping in development of the joint, which at a faster rate because of the increased welding speed, or the development of weld joint with the improved structure and properties. Okay. Then we have the last one where the fusion weld joint to the fusion weld joint is clubbed. So, we have to see like one fusion welding process, one process A is having certain features in terms of the power density, in terms of the shielding of the weld pool, in terms of the area over which heat is applied, okay, in terms of the deposition rate that is realized, in terms of the depth of penetration, and similarly we try to see these processes for another process, these parameters for another process. Say another fusion welding process B may be different in terms of the power density, shielding approach, area over which heat is applied, the depth of penetration that is realized, the width of the weld that is produced, or the deposition rate. So, what we do? We try to bring in the two processes in such a way that they complement each other, help in overcoming the deficiencies related to each other, so that we can help in development of the joint at a higher welding speed and with the improved efficiency, thermal efficiency of the process, higher deposition rate. So, idea here is to primarily enhance the productivity when the two different welding processes are clubbed in together. Okay. So, now we will be trying to see that how the adhesive joining is clubbed with the other welding processes. So, what is done basically, say these are the two sheets A and the B. Okay. And between the two sheets, adhesive of the appropriate thickness is placed. This adhesive is this adhesive can be like the thermoplastic kind or thermosetting kind. Thermosetting kind of adhesives are used for the structural joints where the load will be taken. If just we want to maintain the relative position between the two sheets, then thermoplastic adhesives will also be fine. Okay. So, for structural joints, the thermosetting adhesives are used. Once it is placed, then certainly there will be polymerization of the adhesives, wherein the thermoplastics will simply be converting from the liquid to solid state, but in thermosetting some kind of the reactions will be taking place for the hardening purpose. So, this process of the transformation from the liquid to solid we can term as the curing, during which the joint will gain the strength. Okay. So, there are two terms, like one is the setting time and another is the curing time. In the setting time, we just we apply the adhesive and to place the two components so that they are maintained in a proper position, and thereafter we allow it to harden so that the joint gains the strength. But in this case, what is important is this, that what are the factors that determine the strength of adhesive joint, that is what we have to see now. So, if we see here the adhesive joint, where this is joint is particularly made for development of the lap joint. So, we have to see the shear area. So, in top view, if we see the same joint, it will look like this. Okay, like this is the bottom sheet and this is the top sheet. So, this is the area over which the adhesive bond is created. So, if it is overlap length is L and width of the joint is B, then the area over which the adhesive will be working is L into B. So, L into B will be the shear area. Okay. When the shear area is multiplied by the shear strength of the adhesive, then we get theoretically we get the load carrying capacity or the tensile shear load carrying capacity of the adhesive joint. So, the load carrying capacity of the adhesive joint is determined by the shear area multiplied by the shear strength of the adhesives that is placed. So, higher the strength of the adhesive for a given bond area, the shear area, the load carrying capacity will be high, or if for a given adhesive of the given shear strength, we have to increasing the overlap length for a given B value, our shear area will increase. So, if we have to see this, that let us say if our overlap length is short like this, okay, and for B is the width of the sheets over which adhesive joint is made, and this is the overlap length L1. So, L1 multiplied by B will give us the shear area S1. If the shear area is if the overlap length is enhanced, say from L1 to L2, okay, this is L2. So, for the same width of the sheet, L2 will be greater than our shear area AS2 will be greater than the AS1. So, the point here is we try to increase the overlap length such an extent that it helps in realizing the desired load carrying capacity. There is another logic like overlap length L and the load carrying capacity LCC that increases in this particular manner. So, here it increases, then it becomes constant. Okay. The overlap length does not help in increasing the load carrying capacity further. So, we try to use this kind of the over length. Before that, the joint will be weaker and the plastic strain will be experienced by the adhesive joint significantly. So, our overlap length becomes one of the major parameter in terms of the joint design for the adhesive is concerned. So, but we know that the adhesives have got the limited, adhesives are weak. So, they offer the limited joint strength. Okay. So, the joint strength is limited because of the relatively low strength of the adhesives that is available. So, what we do, we try to combine the strength, say some strength is coming from the adhesive joining or adhesive bonding due to the application of adhesive. The good part is adhesive, the bond will help in spreading the stresses over, spreading the load over the larger area. Okay. So, that will help in increasing the load carrying capacity, increasing the fatigue resistance and help in reducing the stress concentration. So, the fatigue resistance especially is enhanced due to the reduced fatigue resistance is enhanced due to the reduced stress concentration. That benefit is offered by the distribution of the load over the larger area. But since the adhesives are weak, so what we want, like adhesive is the strength is enhanced by hybridization approaches. So, what we do, we use the mechanical fastening based approach. So, we will be introducing either the mechanical fastener in form of like say the nut and bolt or pin. So, these can be pins, these can be rivets or these can be nuts and bolts. So, when the load is applied, this the diameter of the pin or the bolt will provide the desired shear strength. Okay. So, we know that shear strength of the metal is greater than that of the polymer coupled with the shear area offered by the pin diameter or rivet or the nuts and bolts. So, here, so the shear area of the pin or the rivet can be obtained by simply pi by 4 d square. D is the diameter of the pin or rivet or of the nut and bolt system that is being used for. So, in that case, some strength will become offered by the mechanical fastening and combined with the adhesive joining. So, that in turn helps in increasing the mechanical performance of the joint significantly. This is about the mechanical fastening. In case of the fusion based processes like resistance spot welding is made. So, here metallurgical connection is established between the two sheets coupled with the joint strength being offered by the adhesive joint. Okay. Similarly, we can use the metallurgical bond development through the either laser welding or through the TIG welding or any other appropriate heat source can be used for developing the metallurgical joint without using any kind of the filler. Now, we will be trying to see these things in little more detail. Like say this is one sheet, the sheets to be joined by adhesive joining is termed as adherent. Okay. And this is one sheet, this is another sheet, sheet A and B, and between the two sheets we have placed the adhesive, okay, for the adhesive joining, and then it is clubbed with added with the nuts and bolts. It can be clubbed with the rivets like this, and it can also be clubbed with the pins. So, in all these cases what will be happening, wherever there is a pin, nut and bolt or the rivet, that will be contributing towards the strength due to the shear area multiplied by the shear stress related with that particular metal. Okay. So, the adhesive joining combined with the mechanical fastening, okay, that will help in increasing the mechanical performance of the joint, because both will be working in synergic manner. So, what we get if we use just the adhesive joint, then displacement and load curve comes out to be like this. Okay. Suddenly it will fail, but when we club it with the mechanical fastening, then the first adhesive will fail, and then on the failure the load will be taken by the mechanical fastener like the nut and bolt or the rivets or the pins, and then again it will start taking the load. So, here we have the the two different zones broadly. One is the zone due to the one zone is corresponding to the zone where the load displacement curve primarily belongs to the adhesive joining, and another zone where after the failure of the adhesive joint, the another zone comes in where the load displacement curve comes from the mechanical fastening. Okay. So, if we see in totality, say this is the location where the mechanical fastening also fails. So, area under the curve will indicate how much energy it has absorbed in course of the failure. This energy is important parameter with regard to the energy requirement to cause the fracture in these kind of the joints. So, this kind of the joint or hybrid joints, especially the adhesive joint clubbed with the mechanical fastening or the spot welding or the fusion welding, they help in increasing the energy required for causing the fracture. So, this in turn helps in increasing the toughness or the energy, crash energy also, which is required for causing the fracture. That is why this is extremely good for the automotive applications. Okay. So, this is what I have just explained. When adhesive load, when the load is applied only in case of the adhesive joint, load increases, then after reaching the maximum load it fails. Okay. So, but when we club it with the mechanical fastener, then the load is taken by the mechanical fastener. So, this is the joint in zone 2 where after the failure the load little bit slipping takes place, and then mechanical fastener starts taking the load. Okay. So, this blue line corresponds to the only adhesive joint, and then mechanical fastener comes into zone. So, zone 3 load displacement curve of zone 3 primarily corresponds to the mechanical fastener. So, what if there is no gap between the fastener and the sheets? So, what happens when say the fit up is perfect between the sheets and the mechanical fastener, then as soon as the adhesive joint fails, immediately the load is taken by the mechanical fastener, since the fastener is strong. So, load displacement curve comes out like this, and then if the strength is little less, then it will be like this, and if there is a little slippage or clearance between the sheets, then it will load displacement curve will come down, and then the load will be taken by the relatively weak mechanical fastener. So, this is how we can get the variety of the profiles as far as the adhesive joint clubbed with the mechanical fasteners are concerned. Okay. When in the hybrid adhesive joining in say if in the sheets, if you use just one fastener, okay, means there is only this shear area is available. So, our the load carrying capacity and load displacement curve will be like this when just one pin is used. Our load carrying capacity increases significantly, but the elongation is reduced when you use 2 pins. When 3 pins are used, the load carrying capacity is enhanced, but further the displacement is reduced. But when we club it with the adhesive bonding, what we get like this. Okay. So, when the joint when we are using so many mechanical fasteners, then the sheet becomes extremely weak and it does not contribute much towards the displacement. But here when we use 1 or 2 sheet mechanical fasteners, then after failure of the adhesive joint, we get the load, we get the contribution of the mechanical fasteners in load distribution curve. Adhesive bonding clubbed with the clenching, this is the another kind of the mechanical fastenings. In this case, we use the die and punch with the unique profiles, and the 2 sheets are placed, then the punch is applied. So, here the sheets will be moving down. Okay. So, this when they move down, they get deformed, they fill the gap in the die and they deform like this. So, when the deformation takes place in enlarged view, we can see this is the kind of the mechanical interlocking that will be taking place, mechanical interlocking between the sheets that will be taking place, and this mechanical interlocking will help in development of the desired strength coupled with the adhesives. So, what happens when we use the clinch joint of the weak material? Okay, our load displacement curve is like this, where load carrying capacity is very less, displacement is also less. But when we use the hybrid joints, our load displacement curve becomes like this. So, only adhesive performs much better, but combining with the clinching bonding, the load is almost the same, but the displacement is somewhat reduced. But when we deal with the, when we use the workpiece materials which are stronger, then what happens, the clinch joint goes in like this, adhesive joint fails like this. But when hybrid joints, initially the adhesive will fail and then load is taken by the clinch. So, this section indicates this is the adhesive failure, and then our the clenching joint will come into the action, that is corresponding to the clinch failure. So, when we have the low, medium and high strength or high work hardening metals, then our curve changes accordingly. Okay. The mechanical, say, bond fastening, adhesive bonding clubbed with the mechanical fastening. So, here in this case what we do, so adhesive bond is clubbed with the mechanical fasteners like the nuts and bolts, rivets, etc. So, what is the approach of this? Initially this is the sheet, we first create a hole, hole is created, hole is drilled, then what we do, then it is cleaned, hole is cleaned using suitable wire brush and then water jet. Once the hole is created like this, it is filled with the adhesive up to certain distance, and then once the hole is filled with the adhesive up to an identified value, we put the mechanical fastener, that is this. So, adhesive is filled, adhesive is being filled and adhesive is filled up to the desired height, then we place the mechanical fasteners like this and then allow it to set for some times, that is the gel time, so that the position of the mechanical fastener is not disturbed, and then it is allowed to cure. So, here what we get is the advantage of the mechanical fastening coming due to the mechanical fastener, as well as the load also is being taken by the adhesive bond. Okay. So, how this kind of the bonds fail in? So, one is where the shearing can take place in this way of the matrix itself, and then the adhesive can fail or the nut and bolt itself can fail. So, here this is the adhesive fastener interface failure, where the failure between the adhesive, say this is the adhesive and this is the fastener, mechanical fastener. So, the failure can occur from this, that is the adhesive fastener interface failure. Okay. Adhesive failure is one where the adhesive on its own fails. So, if the failure is from this is the fastener, and if the failure occurs from this location, then this is adhesive bond and the fastener interface, and if this is the adhesive, and if the failure occurs from the adhesive itself, then this is the adhesive failure, and it is mixed failure when it is combined, like part of the adhesive failure and part of the interface failure. Okay. And this is the matrix failure, where the matrix adhesive matrix failure, where the matrix in which hole was drilled, and if the bonding between the adhesive and the matrix is not good, then the adhesive matrix failure takes place. Okay. This is the ham flange bonding, commonly used in the automobiles, okay, especially in the doors of the automobiles. So, how it is done? Like, there are two sheets, one is the outer sheet and another is the inner sheet. So, between the two sheets, what we do, we apply adhesive and then the hemming is done. So, what this is how it works. So, this is the outer member, okay, we place the adhesive and then we place the inner member like this, and then load is applied, so that the adhesive spreads. When the load is applied, adhesive spreads like this, and then hemming is done by deforming the outer sheet, so that it helps in development of the adhesive bond between the inner sheet and the outer sheet. So, here hemming provides the mechanical interlocking, and presence of the adhesive provides the desired strength contribution from the adhesive bonding. And normally, when hemming is done, the adhesive thickness is difficult to control the in adhesive. In ham flange bonding, it is difficult to control the thickness of adhesive, because somewhere it is thin and somewhere it is thick. So, this reduces the mechanical performance. Therefore, few approaches have been developed, like use of the adhesive tape, okay, so that the thickness will be uniform wherever the bond is created, or the adhesive with the glass beads. So, this helps in controlling the thickness of the adhesive uniformly. And when the bonding, this kind of the bonding or adhesive bonding is not good, like incomplete adhesive or unbonded zones are there, or excessive adhesive leakage is there. So, then these are like they will either be reducing the appearance or the steam value of the joint which is being made, or they will also be reducing the joint strength due to the unbonded areas. So, these are the various technological aspects related with the hem flange bonding, and they will be governing. These are designed properly and they will be affecting the joint strength. So, resistance is spot welding and adhesive bonding. So, here what we do, say these are the two sheets. So, between the two sheets what we do, after cleaning, preparing the surfaces, adhesive is placed. Then through the resistance spot welding, current is designed, identified current value is applied through the pass through the interface. So, since the R is here high, so what we need? We need little lesser current. So, when the under pressure, current is allowed to flow from the sheet A to sheet B across this adhesive through I square RT heating, because this thickness is very less, maybe 50 to 100 micrometer. So, through the I square RT heating, heat is generated, and that helps in development of the metallurgical joint. And the heat is generated is too much, because we certainly need the melting of the in the thing surfaces of the two metallic sheets which are being joined by the resistance welding. So, in this process of excessive heat generation by the resistance welding, the adhesive is certainly thermally damaged. Adhesive is thermally damaged. So, say if this is the area where we have developed initially our adhesive bond was everywhere, if the spot weld has been developed in this location, then certainly in this area our adhesive will be thermally damaged. So, it will evaporate completely. And the neighboring areas also the thermal decomposition of the adhesive can take place. But other areas where the heating has not been there, their adhesive will remain intact and it will contribute towards the joint strength. So, here in this kind of the hybrid joining, adhesive joint clubbed with the resistance spot welding both contributes towards the joint strength. Okay. Now, this kind of the hybridization can also be done through the TIG welding. So, in that case, like two sheets are there, we apply adhesives, then they are placed in overlapping conditions with the adhesive, and then heat is applied on the top sheet with the help of suitable by controlling suitable arc and welding current and voltage. So, here melting of the top sheet and part of the melting at the bottom sheet is realized, and this in turn helps in development of the metallurgical joint and other areas where the adhesive joint will be contributing. So, this is how, like say, the TIG spot weld bond is developed, and we get the appearance of the TIG spot weld joint of this kind. Okay. When we see the cross section, if we use less heat, then the melting of the lower sheet is limited, but melting of the top sheet takes place completely. If we use a higher heat input, then complete melting of the even second sheet is taking place. This is the zone where the metallurgical bond across the sheets will be developed. In other areas, we may have our the adhesive bond where it will be working. This is the case where partial penetration of the lower sheet has taken place. So, because heat has been supplied in good quantity in order to realize the melting of the top sheet as well as part melting of the lower sheet, therefore, it generates the heat affected zone and the fusion zones also. So, the fusion zone, because of the rapid cooling, results the fine grain structure, while the heat affected zone produces the coarse grain structure because of the grain coarsening, and this is how we can see the fusion boundary, where we can see the fusion boundary, weld nugget and the heat affected zone both, and this is the base metal. So, if we try to compare, because of the excessive heat generation, the base metal is getting coarsened as a heat affected zone, and the weld metal is refined because of the rapid cooling, and this is the weld interface. So, since in this case the steel was welded, so certainly some kind of the hardening hard faces will be formed. So, as compared to the base metal in heat affected zone, the weld zone is harder and stronger. Okay. So, heat affected, so this is the weld zone where our hardness is high, and in the heat affected zone hardness is less. So, this we can say as if this steel was in Q and T condition, then over tempering we can say is attributed to this kind of the softening, or the coarsening of the grain structure can also be attributed towards the softening of the heat affected zone. If we compare the performance of the like the welded joints where we simply develop the spot weld by the TIG welding, okay, like this, then our joint strength is less, load carrying capacity is say around 10 Newton. If we use the bonded joints, means only the adhesive bonds, then our load carrying capacity is around say 13.5 Newton. Okay. And if we combine both adhesive joint and the weld joint, then our load carrying capacity is enhanced further. So, weld bonds where the TIG clubbed with the adhesive joining, TIG welding clubbed with the adhesive joining, this improves the load carrying capacity significantly, and this is attributed to the improved load distribution over the larger bonded area between the two sheets which are being joined. The sheets in the TIG adhesive joint failure, when the load is applied, the failure can occur from the interface. This is one. So, here if the failure occurs like this, then this is interface failure, or if if the nugget is pulled out from one of the sheets, then that is known as the nugget pull out failure, and the pull out failure contributes towards the strength in much better way as compared to that of the simple interfacial failure. Here what is important to see, like around the zone wherever the spot is made, TIG spot is made, around that a black zone is formed, that is due to the thermal decomposition or thermal damage of the adhesive, but around that our adhesive will be contributing in good way towards the external load. Okay. In the laser welding, say here laser weld bonding, since the TIG uses relatively low power density, but the power density associated with the laser is very high, okay, especially for the welding purpose. This is say 10 to the power 4, okay, and this is the interaction time. So, what we do, since the laser delivers the lot of heat in very short time, okay, so if adhesive joint is there and we supply the laser forming the metallurgical bond, then the heat delivery, heat dissipation to the underlying base metal will be very less. Therefore, the damage to the adhesive joint is minimized when the laser welding is used as compared to that of the TIG welding. In TIG welding, we supply lot of heat. So, large area of the top sheet melts a little bit, bottom sheet will melts, and the metallurgical bond will be created certainly, but this will be causing the thermal damage to the adhesive joint to a greater extent, because lot of heat, significant amount of the heat is supplied for developing the TIG weld joint, TIG spot as compared to the laser welding. So, laser welding offers the much better the joint strength and the performance as compared to that of the, so this is laser bonding. So, as compared to that of the that TIG adhesive joint hybridization. Okay. Now, multiple times we also do the hybridization of the fusion welding processes. So, what we do, fusion welding process 1 is clubbed with the fusion welding process 2. When these two processes are clubbed together, when we see that the process 1 is lacking in certain aspects as compared to the process 2. Okay. So, combining helps in extracting the benefits associated with the both the welding processes. Okay. So, if we do not do any kind of the hybridization, then our all the heat input is less, but the welding speed is also less. Our welding volume and heat affected zone is very large. So, all these are undesirable. So, when we do the hybridization, there is a marginal increase in heat input, but there is a significant increase in the welding speed and significant reduction in the weld volume and the heat affected zone. So, our welding speed is enhanced, the weld volume and the heat affected zone is enhanced. So, that helps in improving the performance of the weld joint. This helps in improving the productivity of the weld joints. I will talk little bit about the characteristics of the various processes. Like say we have the processes can be compared in terms of the heat generation, spread of the heat during the heat application during the welding, power density associated with the welding process, and the weld production. So, these are the important aspects that govern the performance of the weld joint when it is developed by a particular process. So, if we see that one particular process heat is applied over a larger area, power density is less, or heat generation is by arc or by plasma or by laser or electron beam. So, we try to see like how the two processes can be clubbed together so that we take the advantages associated with each of process. So, what we do basically, the laser is clubbed with the MIG welding, this is one. TIG is also clubbed with the plasma. TIG clubbing is possible, or like say so, or the laser beam clubbed with the plasma. So, this kind of the clubbing and combination is realized in such a way that we get the advantages associated with both these processes. So, what happens when we work with the low power density? Our weld penetration is less, width is more. Increasing power density increases the penetration, reduces the width, that is what we can see. So, high power density helps in deeper realizing the deeper penetration, but the narrow weld, because the approach of the welding is changes. When we work with the low power density, our approach is melt in mode, but when we go with the higher power densities, then keyholing is realized. So, when the keyholing is realized, we achieve the greater weld depth to the width ratio. Okay. Now, how the hybridization is done? Say this is the main heat source, okay, which is being used for fusion. Then another heat source can be used for preheating purpose or post weld heating. So, depending upon the requirement, we can club the another heat source, or we can place the another heat source at a particular location. So, this is the one where preheating or post heating second heat source is being used, not for the melting purpose, but either for preheating or post heating purpose. Okay. Then now the heat source can be placed coaxially or neighboring to each other, like say this is the one heat source and the another heat source is also in the similar domain. Okay. Or the paraxial, where the axes are same, but they are not on the both are focused on at the same location, but they are not in the same axis. This is called paraxial, and when the two heat source will be supplying the heat along the common axis, then it is known as coaxial. So, what are the benefits that are realized? Like say a laser which is offering the heat delivery over a smaller area, but arc offers the heat delivery over a larger area. Okay. So, when the heat delivery is over a smaller area, like in laser welding or in electron welding, so we need to have very good fit up, otherwise what will happen, the heat will pass through the gap between the, or the beam will pass through the gap between the sheets. That is why it is very important, like if the sheets are rough like this, then during the welding what will happen, if the edge preparation is not good, then the heat source will pass through the gap between the two sheets being joined. So, what we need? We need very good edge preparation in order to ensure that beam supplies the desired heat to both the sheets and parent metals for realizing the melting. But when we club it with the arc welding, like say the arc welding is clubbed with the laser or electron beam, then heat is delivered over a larger area. So, this fit up problem is minimized. Even if the edges are rough, the heat delivery over the larger area, over the wider zone, that will facilitate the melting of the fang surfaces. And so, here the laser will help in realizing the deeper penetration, okay, and the arc will help in realizing the wider bead. So, wider bead helps in reducing the fit up requirement, and the deep penetration will be realized through the laser welding. So, the fit up requirement is minimized, edge preparation requirement is minimized when we combined the laser with the arc welding process. So, the hybridization of the fusion welding process help in fit up, reducing the fit up requirement. It helps in increasing the penetration, because one may be working on the melt in mode, another may be working on the keyhole mode. Keyhole mode allows the deeper penetration. When both work together, our welding speed is enhanced. So, it is also possible, like we can club with the laser welding with the MIG welding. So, MIG will help in applying the filler metal of the desired composition to adjust the weld metal composition as per the need, while realizing the deeper penetration and a faster welding speed. Okay. When the heat sources are used sequentially, then the PWHT of the weld zone can be realized, and the higher deposition can also be realized when the hybridization of the fusion welding processes is done. Now, I will summarize this presentation. In this presentation, basically I have talked about the need of hybridization and the various approaches which are used for the hybridization of adhesive joining clubbed with other joining processes, and the kind of the benefits that are realized by the hybridization of the fusion welding processes. Thank you for your attention.